On today's installment of MatHAMMatics, we are going to dive into coordinate geometry proofs, looking at proving things about triangles. On today's episode of MatHAMMatics, we are going to be looking at coordinate geometry through the lens of triangle proofs. And so how can we prove different things to be true about triangles using some of the prior knowledge that we've gained about what a triangle is, what the different types of triangle are, and how to calculate side length with the distance formula. Our understanding of slope and of the midpoint could also come into play. So to get started, we have triangle AFN here, and we have known vertices of -7, 6, -1, 6, and -4, 2. So let's go ahead on our coordinate plane and plot that. So we can go 1, 2, 3, 4, 5, 6, 7 left, 1, 2, 3, 4, 5, 6 up, and there is point A. We can go left 1 and up 6, and there we have point F, and we can go 1, 2, 3, 4, 1, 2 up, and there we have point N. We can grab a straight edge and we can connect the dots here to form our triangle. And now the task at hand, right, what we're asked to do is to prove that triangle AFN is isosceles. Well, thinking back to our initial lessons about triangles, what does it mean for a triangle to be isosceles? What does this term mean again? And of course, isosceles triangles mean that two sides are congruent. Or we could say they have the same length. Well, with the skills that we have, how could we prove that two of these side lengths are the same? Well, of course, we could use the distance formula, right? Now, just from looking at the triangle, it certainly appears to me that the two that would most likely be the same length would be AN and FN, right? Those are the ones that, to me, certainly appear like they could be the congruent pair. So let's see if we can figure out what the distance of AN is. Well, we know that the distance formula says take the run, square it, take the rise, square it, and then take the square root of the whole thing, right? Well, what is the run from A to N, right? From -7 to -4. The run there is 3. The rise from A to N, 6 to 2, is -4. And so we end up with the square root of 9 plus 16, or the square root of 25, which is 5. Right? So we can figure out that the distance of AN is 5 units long. Well, in order to prove that this is an isosceles triangle, then we would need to find then that the distance of either AF or FN is also 5 units. Well, we can calculate right away that this is 6 units long, right? That one's pretty easy to do. So it's not congruent with AF, but let's check and see about FN. Again, let's think about the rise and the run. Okay, grab a different color here to distinguish what's going on. So from F to N, from -1 to -4, our run is -3. The rise from 6 to 2 is actually identical, right, as the first one. And so you can see right away that we're going to end up with the distance of Fn is also 5. Since the distance of Fn is 5 and the distance of An is 5, we can now say we have proven that we have an isosceles triangle because we now verified, right, through our algebra that An is congruent to Fn. And since this is true, we can now say we have proven that AFN is isosceles. So what about another example? What's another way the distance formula could help us out? Well, in example 2 here, we have triangle MEP, and the vertices are given here. So again, I need to mark out where my origin is because it didn't show up on this document. So M is at 612. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there is M. We've got 6, 4 is where E is. So again, that's going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So there is E. And then 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. There is point P. And so again, we can grab our straight edge and we can sketch this in. And so the question is, can we prove that this is a right triangle? Right, so a right triangle that is not isosceles. Well, how would we have to prove that? Well, in proving that it's a right triangle, what is the one key distinction to being a right triangle, right? What does all right triangles possess? Well, of course, that's a right angle. Oops. Get away from me there. All right triangles have a right angle. So how could we prove right angles? What do we know about lines, the way that they meet, and right angles? Think back to semester 1. Perpendicular lines meet at 90-degree angles, remember? And so how can we prove perpendicular lines? Well, remember that perpendicular slopes are simply opposite reciprocals. So if we were to look at the slope of PM, for example, right? The slope of PM. Well, the slope of PM, we can calculate the rise, right? So from M to P is -4, right? From 12. I'll bring this down here so we can see it a little bit more cleanly. There's point M and point P, and so there is a drop of 4 for the rise, a drop of 3 for the run, right? And so we would say that this is a slope of 4/3. What is the slope of PE? Well, again, we have the point E right here. We have the point P right here. The rise from 4 to 8 is positive 4. The run, negative 3. So as we look at these 2 points here, right, this we would just say has a slope of negative 4/3. Are these opposite reciprocal slopes? Well, they are certainly opposite. The sign is different, but what is a reciprocal? A reciprocal would mean this is flipped over. And so these are not opposite reciprocal slopes. Therefore, these are, not perpendicular. Therefore, we can prove, right, because there's no right angle here, we can prove that, triangle MEP is not a right triangle. Okay, so because we were able to demonstrate that there are no perpendicular lines, that means we can't have a 90-degree angle right here, and therefore this is not a right triangle. Now let's take a look at the side links here. What do you notice about the rise and the run for both of these situations? Well, the rise and the run really seem to match up pretty nicely, don't they? Right? If we were to figure out what the distance of PM is and the distance of PE using our distance formula, right? Well, the run is 3 squared, the rise 4 squared. We would end up with 5, right? Or if we had done PE, we would have a run of negative 3 squared and a rise of 4 squared, still with 25 under the square root, which is 5. Now, what does this communicate to us? We'll think back to exercise number 1, right? That means that we have an isosceles triangle. So in essence, this question is almost backward, right? Not only can we prove that it is not a right triangle, but we can prove that it is isosceles, okay? So in some instances, what we're going to find through going through and completing these proofs is that the information we thought we were looking for is actually not going to be the case, but in fact, the opposite is true. But utilizing these skills of understanding slope and understanding the distance formula, we can prove these things to ourselves. So there are 4 proofs for you guys to try here on the next couple of pages. And if you have any questions, please reach out for office hours. Have a good one.